our discussion with Abelian groups. So far what we have learned is we have seen definition of groups and some examples. In particular, we have seen example of the group Z, the Abelian group Z plus, and we have seen the example of the group Z mod and Z plus, and these are going to be in some sense the most important groups that will come across later in this course. And we have seen the definition of group homomorphism. Isomorphism, kernel of a group homomorphism. We have also seen the notion of subgroup of a group. And we have seen criteria how to check when is a non-empty subset of a group is a subgroup, when is a group homomorphism an isomorphism, or how is the kernel of a group homomorphism being 0 is equivalent to the group homomorphism being injective. So last thing we discussed is that if you have two abelian groups A and B, then the set of homomorphism between A and B becomes an abelian group. So let us see an example of this. So you take the group Z plus the usual abelian group and Q plus, then you consider the group home of Z and Q. So we said given groups, how can you construct more groups? So this was one example. If you have two abelian groups, you consider the set of homomorphism between the abelian groups, and that forms an abelian group. So you have here Z and Q plus with the usual abelian groups, and the homomorphism between Z and Q forms an abelian group. So if you have two homomorphism F1 and F2 from Z to Q, then F1 plus F2 is a map from Z to Q. How it is defined? F1 plus F2 at an integer n is F1 of n plus F2 on n. This was the definition of, we discussed of group homomorphism last time. So adding two group homomorphism last time. So this is consistent with that. And then you can check that this is actually a group homomorphism. And moreover, one thing to notice, if you have a group homomorphism from Z to Q, so with this addition structure, so pointwise addition, this becomes a, so these are the elements of homomorphisms, and that's how you add them. This is an operation. There is a map 0, which takes every integer to 0, right? So that is the identity map, and this F1 plus F2 plus F3, whichever you add in the definition will be the same. F1 plus F2 will be equal to F2 plus F1, and given any F1, there is a map which is minus F1, whose value at n is the value of F1 at n, the negative of that. So that will add F1, and minus of F1 will add to 0. So that means this forms an abelian group, and this is the example. If you remember, we discussed last time in the last video. This is what we have discussed. So here we are taking a particular example of the first group being Z and the second group being Q. Okay, so now note that, so let us try to understand what this group is actually. So if you have a group homomorphism, an element of this, right? This is the operation. What are the elements in this group? The elements are group homomorphism from Z to Q. So there is, given two groups, there is always a homomorphism. For example, you send everything to 0. So let's say F is a group homomorphism. Then what is the value of F of 2? 2 can be written as 1 plus 1, and since it's a group homomorphism, it is F of 1 plus F of 1. So it is 2 times F of 1, right? Similarly, if you take a positive integer n, then F of n is F of 1 plus F of 1. So this is, if you like, this is F of 1 plus F of 1, which is F of 2, sorry, which is also F of 2, but it is also equal to is also equal to 2 times F of 1. So similarly, if you have any positive integer n, then F of n will be n times F of 1. F of n will be F of 1 plus 1 plus 1, n times, and then it will be f of 1 plus f of 1 n times, so it will be n times f of 1. And you can check f of minus 1 is minus of f1. That is because f of 0 is 0, and f of 0 is equal to f of 1 plus minus 1, and f of 1 plus minus 1 is f of 1 plus f of minus 1. And f of 0 is 0, so you get f of minus 1 equal to minus of f1. Right? So maybe I can work this out here. You have that f of 1 minus 1 equal to f of 0, and we know f of 0 is 0. This is one of the things we mentioned last video. And this is equal to f of 1 plus f of minus 1, right? So that means, so this shows that f of minus 1 is minus of 1. Right? So more generally, then if f of n equal to n times f of 1 for a positive integer n, and if you have that f of uh, minus 1 equal to minus of f of 1, then from there you can easily deduce that f of n equal to n times f of 1 for any n in Z. So once you know f of 1, then you know a value at f of n, just n times f of 1. On the other hand, f of 1 can be assigned any value in Q. If you can think about it, if you have a group homomorphism, there is no restriction on what value f of 1 can take, right? So you can assign f of 1 0, f of 1 1, f of 1 equal to p by q, any value you like, 1 by 2, 2 by 3, minus 4 by 5, there is no restriction. So using that, we can see that what I mean, once you assign a value, a particular value, then that f is, once you decide what is f of 1, there is no restriction. You can decide. Once you decide f of 1, then that particular f gets determined by that particular value. It is any value at any other integer n times the value at whatever value you have chosen at f of 1. So then you can see home of zq to q, f sending to f of 1 is actually, uh, so you can see that this is one can actually check that this is an isomorphism of groups. So you are sending f to f of 1, and you are sending, so g to g of 1, excuse me, g to g of 1, g to g of 1. So this is a map taking an f to f of 1. This is a map, g goes to g of 1, then f plus g goes to, this implies f plus g goes to f plus g value at 1. So this is a group homomorphism. And if you think for a moment, this will be surjective. And if f of 1 is 0, then f is identically 0. So this says that this one, if of 1 can be assigned any values, this says that this map, so let's call this map, give it a name phi. So phi of f equal to f of 1. So this says that phi is in, so this one says that phi is surjective. And this one, f is determined by f1. This one says that f phi, sorry, says that phi is injective. Phi is injective and phi is surjective. So we get that is an isomorphism. You get that this is an isomorphism. So home of Q comma Z is actually isomorphic Q. Okay, so we get that, if you like, home of Z comma Q, this abelian group is isomorphic. So this is an example of understanding isomorphism, the group homomorphism, and understanding maps between Z and Q, which are group homomorphism. Okay. So let us move to a slightly different topic now. So order of an element. Okay, so let's say A is a group, and you have an element A in the group capital A. Then order of the element A is the smallest positive integer n, such that A to the power n equal to E, where E is the identity in A. And now that we are getting used to groups, we are not going to write this operation symbol. We are just going to sometime, if we write A to the power n. So what is the meaning of this? So this is the meaning that A to the power n means, A to the power n here means A composed with A composed with A n times. N times, okay. And this E is the identity on on A. So once we are, because we are getting to ease the notation, we often will just not write this. We'll just write A to the power n. Or sometime if we use additive notation, we'll also write n times A. And this E, sometime we use E, which is the identity on A. Sometime we use 0A. If we write multiplicatively, we'll also write this is equal to 1, where 1 means the identity on A. And if you write or if we write additive, sometimes we write 0 or 0 times A. So they all have the same meaning. Once we get used to the notation, slowly we'll be more relaxed and we'll write 0 and 1 and things like that. But you'll understand it from context. What does it mean? Okay, so uh, such that A to the power n equal to E holds. So if so, the here there is a catch that if it exists, okay, if it exists. So if no such integer exists, then we say order of A infinite. Okay. So let me again recall. Order of an element in a group is the smallest positive integer n, such that A to the power n, A composed with A composed with A in the group operation n times, you get the identity element of the group. If no such element, if no such n exists, no such integer n exists, then we say that the order of A is infinite. Okay. So on the other hand, there is a related terminology. Order of a finite, if a group is finite, then order of a group by definition is the cardinality of the set A, okay? The number of element in the set A. So these two concepts should not be confused. So order of an element in the group is the number of smallest positive integer n, so that A times n. If I compose n times in the group operation, then I get the identity element of the group and is the smallest such integer. Of course, we'll see examples. On the other hand, order of a group is by definition the cardinality of the group. Okay, so let A plus be a group and Y is in A. If order of Y equal to n, so let's see some example. Here may be a good place to pause and see some example. So example, you take A equal to Z with respect to the usual addition. Then so if n belongs to Z, then so let's say if m belongs to Z, then it is the smallest integer n, so that n times m equal to 0. 0 is the additive, right? But there is no such. So if m is not equal to 0, then there does not exist a positive integer m such that n times m equal to 0. This implies that order of m equal to infinity for m not equal to 0, and order of 0 is equal to 1 because it's the smallest positive integer for which n times 0 equal to 1 is satisfied is n equal to 1. So by definition, order of an identity element is tautologically it is equal to 1. So so yeah, so order of an element is order of an element is um, in integer z, order of every element is infinite other than the identity element, which is 0. On the other hand, let's say another example. Let's say b equal to z mod n z plus, where n is some integer. Then what is the order of an element of the element 1? So 1, if you multiply, so it has to be the class of 0. So let's say m times 1 equal to 0. That means 1 plus 1 plus 1. So this implies 1 plus 1 plus 1 m times is equal to 0. That means m equal to 0, right? So that means n divides m. So, what will be the smallest possibility? So m equal to n. So in z mod nz plus order of 1 equal to n. Okay, where plus is the addition of equivalence classes we have defined. Okay, so so this is one in z mod nz order of 1 equal to n. Okay, so this is another example, and in fact, you can check in a finite group. Every element is of finite order. Okay. Next is we continue with some facts on order. So one of this fact is this, that if you have an element, if you know the order of an element, uh, so if A is a group and Y is an element of A, and suppose order of Y is finite and is equal to n, then order of Y to the power n, m is equal to n by GCD of m comma n. You can check this. This is not difficult to verify. So using this exercise, you can now check what is the order of an element R in Z mod nz for any R, right? Okay, so next is, so this is the definition of order. Order of y to the power m equals to n divided by GCD of m. Next is the generator of an abelian group. Next concept is, so we understood what is order. Next, we discuss what is the generator of an abelian group. So let A plus be an abelian group. Then a subset S of A is said to be a generator. So we'll see. We'll come back to order and we'll see why. We'll see what is the significance of order. We'll see later, and it will be important for our application also. Okay, so a generator of an abelian group. So if A is an abelian group, and then is this, so what we want to understand. So a group may be finite or it may be infinite, but sort of if especially if the group is infinite, for example, Z is infinite. It is we want to understand what is the minimal number of elements from which every other element can be generated, and that leads us to this definition of generator of an abelian group. So let A plus be an abelian group, then a subset S of A is said to be a generator of A if every element of A can be written as a finite product of the elements of S and their inverses. So if Y belongs to A, okay, so implies Y equal to S1 S2 to SR, where either SI belongs to S or SI inverse belongs to S for I equal to 1 to R. So this R depends on Y. So, 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 so every element can be written as finite product of elements coming from S or their inverses. Okay. So we'll see more example, then it will be a bit more clear probably. But so if you understand the definition, then every group has at least one generator, one set of generator. Namely, you take the whole group, right? So that is also a generator. So, but that is like the largest possible generator in some sense. So, of course, one would be interested. More interesting would be what is the minimal set of generator. Now, uh, so because we are, as I said in this, so this leads us to the. So we are only dealing with abelian groups in this case, and we can say a bit more. But more interesting would be for us the groups which are at least as a which are called finitely generated abelian groups. So what are finitely generated abelian groups? So a group, an abelian group is said to be finitely generated if there exists a finite set, an abelian group A. Let's just give it a name. A is said to be finitely generated if there is a finite subset S of A such that every element, so let's say, so once again let us be, let's say is equal to fix finite subset S1 S2 ST, every element Y belong to A can be written as Y equal to S1 prime S2 prime SR prime, where, or let's say, simplify notation maybe X1 X2 XR, where Xi belongs to S or Xi inverse belongs to S. But as A is abelian, we can in fact write, if you think for a moment, we can write Y equal to, so we can collect. So if X1, let's say X1 is S1 and X3 is S1, then we can put it S1 squared. Then if X2 is S1 inverse, then S2 inverse, then we can put it S2 inverse. So we can collect whatever S1, S2 are there. So we can write Y equal to S1. So we are using multiplicative notation here. So here this dot means group operation, right? So x1 dot x2 meaning multiply. So we can just write s1 to the power n1, s2 to the power n2, and st to the power nt, where ni belongs to z. Why it is belongs to z? This is important. It belongs to z because we say that either si either x each of these elements, either they are in S or their inverses are in S. So that will be reflected by, we write it as ni belongs to either, ni can be positive, ni can be negative, or a particular element may not be there. So then you put it Z. Okay, and if you use or if you use, excuse me, or if we use or if we use additive notation, then every element can be written as every element y can be written as every element y in A can be written as y equal to n1 s1 plus n2 s2 plus nt st, where uh, ni belongs to z, and this ni depends on y. Right? So there is a fixed set of finite set S1, S2, St. Each Si is an element of A, such that every element can be written as N1 times S1 n plus N2 times S2 plus Nt times St. If you use additive notation, or this just means S1 composed with itself N1 times, or if it is negative, then it means minus S1 or S inverse composed with itself N1 times, mod of N1 times, like that, right? So this is the so this is important for us. So every element can be written as some combination of S fixed element S1, S2, S2, Z linear combination of that. So if you write multiplically S1 to the power N1, S2 to the power N2, S2 to the power Nt, uh, or so, and these Ni's are in Z. So this is the definition of a finitely generated abelian group. So in particular, cyclic group. So a cyclic group is a finitely generated abelian group. Abelian group. So we can directly say is an abelian group which is generated by a single element y in A, or single element S in A. So that means every element so there exists that is equivalently, that is there exists an element S in A such that every element looks like every element X in A can be written as X equal to S to the power n for some n in Z, or additive notation. In additive notation, n equal to x equal to x equal to S2 in times S for some n in Z. So what are the examples? First example is Z. So every element, if n belongs to Z, if n belongs to Z, this implies that n equal to n times 1. So that means Z is generated by this element S equal to 1. So one writes in this case that Z equal to 1 generator. So one writes A equal to S1, S2, ST. So similarly, Z mod and Z you can check is generated by the class of 1. Every class can be written as sum n times this. So Z mod and Z is another cyclic group. This cyclic group Z is infinite and is generated by 1. This cyclic group Z mod and Z, as we have seen, it has n element. It is also generated by the class of equivalence class of 1. Okay, so also notice that, as I said, Z itself is a generator of Z. So generating set is not unique. If it's called cyclic, it doesn't mean that every, so it's cyclic means there exists a generator. There exists one such element which generates the group, but it's possible more than one element will also generate the group. Okay, so yeah, so this is the example of cyclic group. So one of the thing is that, so what kind of groups are cyclic groups? So one of the thing that we'll see is easy to see any two cyclic groups of same order are isomorphic to each other. So in some sense, cyclic group are the simplest kind of groups. And so what do you want to see? That any two cyclic groups of same order are isomorphic. So how do you prove that? So suppose you have a infinite cyclic group, then it is easy to see is isomorphic to Z. And if you have a finite cyclic group of order n, then it is isomorphic to Z mod nz. I'll leave the details for you, but you can check it. Okay. So next is a couple of basic results about cyclic groups. We'll recall that every subgroup of a cyclic group is cyclic. Okay, so if you have a cyclic group H, cyclic group A, and if H is a subgroup of the cyclic group, then H also must be cyclic. So in fact, if H is not equal to identity, and if A is generated by, let's say, X, then you can tell how it is a cyclic group. It is generated by the single element x to the power d. What is the d? D is the smallest positive integer such that x to the power d is in H. Okay. So you can check that x to the power d will generate H. So this is not only it tells you that every subgroup of cyclic group is cyclic, it also gives you an this exercise tells you how to identify the generator of this. So then H is generated by x to the power t. Okay, you find the since the group is generated by cyclic is generated, it has a single generator, namely let's say x. Then every element looks like some power of x. So if d is the smallest positive integer such that x to the power d is in H, then you can write H is generated by x to the power d. Okay, and if A is a cyclic group of order n, then for every positive integer d greater than equal to 1 and d divided in n, there is a unique subgroup of order d in A. So there is a unique subgroup H of order d in A, and in fact, if A is generated by x, and then H will be generated by x to the power n mod d. Okay, so so if you have a finite cyclic group, as I said, it is isomorphic to Z mod nz, and the order of the uh, order of the element will be order of the generator will be the same as the order of the group. Okay, where order of the group refers to, as I said, the cardinality of the group. So there are two things we are proving here. One is that, or I'm leaving you some checking to do, that every subgroup of a cyclic group is cyclic, and if d is the smallest positive integer, so that x to the power d belongs to that subgroup where x is generator of the group, then H is generated by x to the power d. On the other hand, for every positive divisor d of n, where A is a finite cyclic group of order n, there is a unique subgroup H of order d, and that subgroup is generated by x to the power n mod t. So in summary, so a group is finitely generated if there is a fixed set of generators, so that every element x can be written as some combination. So let's say there is a finite set S1, S2, St, then every element can be written as x1 to the power n1, x2 to the power n2, x2 to the power nt, where these ni's are in Z. And if there is one particular element which generates the group, then you call it a cyclic group. It is a single generator. The examples are Z, infinite cyclic group, and finite cyclic group order n. One example is Z mod NZ. And these are the only two examples. Any infinite cyclic group is isomorphic to Z. Any finite cyclic group of order n is isomorphic to Z mod NZ. And for every subgroup of a cyclic group is cyclic. And for every divisor n of a group, every divisor d, if you have a cyclic group of order n, for every divisor d of n, there's a unique subgroup of that cyclic group of that order d. And in fact, you can identify the generators also. So these are some basic facts about cyclic groups we learned today. Next time we'll continue some more basic things of group theory. Thank you.